So let's go. I'm gonna go over most of the codes and give a brief explanation of all of them. So here we have the CPP code, okay? This CPP is a different strategy than the one that we have been using. Most of us have been using Java for the pre-rendered skills and the skills challenge. And my idea for this one is for us to switch to C++. C++ works better, is an easier environment to use. It works better with the robot, it has a better performance. And we have more information, more data, more resources, libraries that we can use and we can take from the internet. Okay. The main difference from this code to the one that we are using Java is that I don't have that loops anymore. I'm not talking about commands. I'm not talking about cases, switch cases. Now it's pure C++. Okay, so I have line by line. It's a sequential code where I run line by line. So I execute one command, one instruction. After executing this one, I go to the next one. Okay, so from my point of view, that's an easier way to work. So everything I need regarding this function is going to be run before going to the next one. I don't need to worry about timed loops, about synchronizing instructions. I just call the functions. Okay. To make everything work, I need to start the mock.ds that will basically enable the robot without the command base, without the control panel, without the control station. Okay, it will, the code by itself will enable the robot. Here, to facilitate, to make it easier, we're gonna use some classes. You can create as many classes as you want. Here, created two as an example. One that will handle the hardware stuff and one that will handle the movement stuff. So all the functions related to the movement will be in movement. Everything related to hardware will be in hardware. Whenever I want to use any resource inside that, I need to do hard dot whatever I want, move dot whatever I want. Okay. Hard is an object of hardware, move is an object of movement. Movement is a class, hardware is also a class. Okay. Here, that's the main code where the main logic will happen, instruction by instruction. So the first thing would be these initializations here. I go to the start button. So before anything happens, I'm stuck in this while loop. Once I press the start of my robot, I'm gonna release the code and let it go to the next instructions. I turn on the LED. So again, if I need to use anything related to hardware, I need to do hard dot whatever inside hardware. Later, I'm gonna show you what's inside the hardware. So I set the running LED to true. I set my robot position to 0, 0, 0. First 0 here is X, second is Y, the third one is my robot angle. If my robot angle is 0, it means that my robot is aligned to the X axis. Okay? Then I do position driver. Position driver is a common name for the function that you drive a robot, that will make a robot go from point A to point B. So in this case, I will go from point 0, 0, 0, and I'm going to move to the point 100, 0, 0. Basically, my robot to move straight following the x-axis. Okay. Then my robot rotate to 90. Then my robot move up in y. Then my robot rotate to 70. Then my robot moving x, rotate again, and then moving y. If you are talking about a robot that has 3 wheels, Omni robot, I don't need to. I can combine linear with angular. So here I'm doing first, I move in X to then rotate. Because I'm here in my case, I'm using an omnidirectional robot, I could do this, a robot to perform both movements at the same time. What's not true for a differential robot or any other type of robot that's not omni. Okay. So basically my robot here performs a square movement. Okay, and then turn off the LED, return 0 to finish the code. To run the code, I need to deploy. Okay, all this information, I know that some teachers are new, but all this information you can find here in the Studica website. Let's see if it's not sharing. Anyways, you guys can see well the screen.
Yes.
Yes. Okay. But my question, when I record, it's gonna show like shown to me, or it's gonna show like shown to you guys? That's my question, man. Because for me, this doesn't show the presentation. Shall show what I mean. So that's the Studica website where I have all the information I need. So for example, for installing the software, I have it here right in the beginning where I can install all the dependencies, all the softwares I need, as well as I'm using. After installing all of it, you can start to use the code that I provided to all of you. Okay. To run the code after connecting to the robot Wi-Fi, I can come here and deploy it. Okay. And then it's gonna run my robot. So let's go over the code we have. I have hardware and I have movement. In hardware, I have the hardware interface. So through this class, I will be able to control and read information from my hardware. So if I call the function, the method get left encoder is going to return to me the encoder count of the left encoder. If I do get yaw, it's going to return the angle that the gyroscope is reading. Okay. But through this guy, I can make the interface between the hardware. In movement, I have the movement functions, movement methods. Just like I have movement in hardware, you could create the OMS, which is the gripper. You could create a specific class for the sensors, for the camera, whatever. You can just copy can replicate the steps that fall for these guys, create the class of this guy. The class is defined here, the header file. So in CPP, I have CPP files where I have the definition of functions and variables. I have the header file that store declaration of them. Okay, so here's the class movement and its definition. In the header file, I put the product function of the methods. So for example, here I have the product function position driver. Product function is like the header of the function. It's not the function itself. We just mentioned that inside movement, I have a method called position driver. Where is this position driver defined? Defined in movement.cpp. So if I come to movement.cpp, here I have the definition of position driver. That's inside the class movement. And here's all the code inside it. Okay. So in movement, I have the position driver to navigate my robot from one point to another. I have the method inverse kinematics, okay, that takes the speeds and make it and relate it to the how much I need in each wheel in order to perform these speeds here. I have the forward kinematic, which is the opposite, so it takes from the wheels and translates into x, y, and th. I have the wheel speed that translates from the encoder ticks. Okay, so I have the encoder ticks and translate into the speed of the wheel, centimeters per second. I have set position to redefine a new position on my position driver, and I have shuffleboard update, which is for updates on the shuffleboard some main information. You can put whatever you want. Get X, return the X of my robot. Get Y, return the Y. TH, return the TH. Okay. Position driver, how it works. I have a desired X, Y, and TH, and the idea is to drive my robot to this position. To know how much I need to move to drive to this position, my robot has to know the current position. Okay, so the initial part of position driver is my robot detecting the current position. So here I take the delta encoder, which is the displacement of encoder per loop. I calculate the speed. So from ticks, here I get the ticks, here I get the speed in centimeters per second. So now I have the three speeds of my wheel. So while my robot's moving, I'm calculating the speed in each wheel. In this way, I can calculate later its placement. I sent these speeds to the forward kinematics. The forward kinematics will say to me, if, let's say, for example, my left wheel and my right wheel are moving, it means that my robot is probably going forward or backward. And for kinematics, is the one that will tell you that whenever left and the right motors are rotating in opposite direction, the robot is moving in X. And use the X that is inside forward kinematics. If you go to forward kinematics here, you see that the output here is Vx. This Vx comes through here. What's Vx? Is the speed in the x-axis of my robot. Speed times time will be displacement. So it's how much my robot is displacing, is moving per loop, per iteration of the while loop I have. If I sum all the displacement, it's kind of like an integral. If I sum all the small displacements my robot has, I can take the total displacement, which is my robot position since the beginning of the movement. Okay. So here I have the x of my robot, y of my robot, the angle of my robot. All of them took from the speed, the axle that came from the speed of the wheel that came from the ticks of the input. Okay, so now I have my robot position. I use this information to compare to my desired position in order to know how much to move and where to move. So here I do x diff, which is the desired minus the current. I basically here I'm taking the vector, right? So how much I want to move x, how much I want to move y, how much I want to rotate. I translate this information, the displacement into speed. So here basically what I'm doing is I'm gonna do a proportional math here. So if I'm if I'm more than 10, well, let's say if I'm 10 centimeters to my goal, so if I'm 10 centimeters far from where I want to be, I'm going to be in maximum speed. Okay. So it will be 10 over 10 times maximum speed will be maximum speed this guy. And any other distance less than 10, you make this speed here be less. So for example, if I'm 5 centimeters from my goal, 5 over 10 times maximum linear speed will be half of maximum linear speed. It means that while I'm getting closer to my goal, my speed of my robot is getting less until zero. When is zero? When I'm exactly above my goal. Okay? If here the speed of my robot is more than this distance, 10 is a distance that you can change. You can put 20, you can put 5, whatever works for a robot. But here in this example, if it's more than 10, it's going to be more than the maximum linear speed. And then in this if, to make sure that your robot will not ever go more than the maximum linear speed. This for x, this for y, this for ph. Here, if a robot reach the tolerance, so if a robot is less than, let's see, the tolerance, the header file. The inner tolerance is 4 centimeters. The angular tolerance is 3. So if my robot is less than 4 centimeters in x and y and h, all the speeds will be 0, and then I will get out the while loop. So I will finish, I will work the goal. It means that I reach where I want. Okay. So here I calculate the speeds I want in x, y, th, but what I apply is not x, y, th. What I apply is speed to the wheel. So somehow I translate from x, y, th into speed, into wheels. Who does that is the inverse kinematics. So it takes x, y, th through the inverse kinematics. It translates this x, y, th into back, left, and right. So how much I need to apply in each wheel in order to perform this movement. So for example, if I want to move in X, I need to move left and right speed wheel. Okay. So I calculate how much to apply to each wheel, translate from centimeters per second into PW1, because when I apply speed to the motor, I don't apply the speed. I apply a power. I apply PW1. And PWM goes from 0 to 1. So what I do here, I divide the desired speed in which wheel by the total. This 70 here is the maximum speed the motor can reach when I apply one. If I apply full power of my PWM, my motor will give me around 7. It depends on the robot, depends on the weight of the robot, depends on the displacement of your wheels. My robot 70 works, most of the robot 70. Okay, and so I translate from centimeters per second to PWM. And then I apply this PWM. Okay, so here I'm applying left, back, and right. Here, when I press the stop button, I apply 0 to all the wheels. Okay, here I put this brake, we can remove. Okay, don't need this brake here. This brake means if you press the stop button, you kind of abort your code. You're going to skip all the position drivers and you're not going to perform any other movement. If you remove the brake, the robot will only stop. Once you release the stop button, the robot will back to move to keep the same track, to the same path it was going before. I call the shuffleboard update to update those variables on the shuffleboard. Okay, and then here I just make sure that would be 0 on the wheels. And now that's it. Simple, easy, easy. Okay. I can call as many position drivers I want, like I did. Any questions so far? No questions? Everything clear? Okay. Let's say I have a robot with 3 wheels, 4 wheels, 5 wheels, 1 wheel. What would I have to change here? Mainly, I have to change the kinematics. So the kinematics I put here as an example, they're kinematics for 3 wheels robots. Okay, so I have a back, a left, and a right speed. If I'm talking about a robot with 2 wheels or 4 wheels, the kinematics would be different. I would have a different equation. Okay, which are simple equations you can find on the internet. I have to change it here. So for example, 2 wheels, I only have left and right, but this equation here would be different, slightly different. And also for the forward, this equation would be different. Okay, and that's what we change for different robots. Here we have some parameters. So that's the maximum linear speed I want my robot to reach, which is 30. That's the angler. It's up to each robot. Your robot might want more, might want less. Depends on your robot and the requirements you're looking for. Okay. So now, let's see. Let's see. So here, can you see on my camera? If you take a look at my camera, I'm showing one robot. Okay, that's the robot I'm going to use as an example for us to test the code later. Okay, so it's a robot with 3 wheels. That's the one that use. That's the one that won Emirates Guild. Okay, it has 3 wheels. A tiny robot has 3 wheels, and then we're going to run this code into this robot. First things first, the first thing we're gonna do in this code is your robot is not the same as mine. Because it's not the same as mine, each robot doesn't have the same pings. So I need to make sure that the pings I'm gonna use will be the same in the code. So for example, if I come here to constants, here you see some variables related to the pings, to the connections of the robot. So for example, I have inputs, start button, stop button. I have outputs, running LED, stop LED, and I have the motors, 4 motors, 3 for mobility, 1 for the figure. Okay. Here in hardware, I also have the here's where I use those constants, right? So here I have the start button that you define there, stop button that you define there. If you want to use a servo motor, in my case here, I just put number 9. It means that I want to use the number 9 PWM of the output port of the BMX. You could also create a constant here, constant. Let's call, or you could call servo gripper, servo elevation, whatever, and call it here. Or you can put it straight. Actually, all of them you could put straight. So instead of setting start button, you could put here 12. Okay. This robot I'm using has different pins. So I'm gonna come here. I'm gonna check my robot. And according to my robot, I'm gonna put here. So for example, my start button of this robot is 11. My stop is 10. My running LED is 13. My stop LED is 12. My left motor is 1, 0. My right is 2. And my elevator is 2. Okay, so now once I run, probably gonna work. Shall let me remove the brake here, save. Okay. Once everything is ready, I'm gonna put only one movement just for us to try. I wanna see if you can take a look at the wheels. To run, we can deploy. I don't have many ways to deploy. You can do Shift F5. You can click here and deploy. You can do Ctrl Shift P. All of these related to the environment you can easily find on the Studica website. So my robot is not connected. Okay. Why not? It's deploying. It's deployed. My robot. And is waiting for the start button, which is the first instruction of the code. Once I press, my wheel moves until my robot reach the 100, 0. You couldn't see probably, but both the back wheel didn't spin, but the two front wheels, they did spin. Let me deploy again. Here, deploy. If you take a look at my camera I'm showing the robot. So I deployed. Once I press the start, both wheels front, which is to move in 0, which is to move front, and then stop. If I add all these orders here, we're always going to perform one by one. Let me put on the floor and then we can visualize here. Start, and if it wrong happen, I can press the stop button and stop. So my robot will perform instruction by instruction. First one is the 100 0, then 100 90, then 100 100. I'm rotating to 7, 3, 8, 8. And go 0, 100, then rotate. Then go to 0, 0. Perform all of that. Any question so far? Any question related to the mobility? Because I'm gonna.
Felipe,
Yes.
so in this code, so if you require him to move in the X and Y direction at the same time, is it able to do it for this the drive?
For a Omni robot, when you try. Are you guys seeing the code here?
Yeah.
Okay, so I'm gonna do comment.
Felipe, I think the microphone is away from you.
Better now?
Yeah.
Better?
Yes.
So I'm gonna put here 100, 100, for example. Okay, so my robot. So start with 0 and then go to 100, 100. I'm gonna remove
Mhm.
the start button, then I don't have to. Set my camera. Point. And then keep that's going on diagonal. And then stop. Move the X
Okay.
and Y at the same time. You can move the X, Y, and rotate at the same time for only robots. So true
Okay.
wheels like mine or mechanical robots would also work the same.
So you said this would work for X drive configuration?
X drives with 4 wheels, you mean?
Yeah.
Yeah, supposed to.
Okay. Thank you.
If it's omni, like mine, where the wheels they have an angle, right?
Yes.
Actually, any kinematics you use, my code will calculate to drive diagonal. But according to the kinematics, a robot will not be able to perform. So for example, if I put a robot with 2 wheels, a 2 wheels robot doesn't have a side movement. So my code will apply speeding X, will apply speeding Y. But because this 2 wheels robot doesn't have a Y speed, it could only move X. Okay? Because if you take a look at the movement code here, it's independent. X doesn't depend on Y. So I calculate both. And then I apply both to the inverse kinematics. And then according to what happens inside the inverse kinematics, I'm gonna say if it's gonna work or not. Okay, anything else?
Yes, Philip, how are you?
Are you good?
Sorry, I didn't join from the very beginning, but I just want to make sure. I'll watch the recording later, but did you like cover where to navigate through this navigation pane? Like, how do you start? Because there are some files that we shouldn't be playing with, right? So that we don't have many errors while deploying.
Yeah, actually, anything you change, you are have the risk of causing an error, right? If a robot has 3 wheels, you don't have much to change actually. You have more things to add, but to change you don't have to worry about. Mainly, if you're using a 3 wheels robot, you don't have to worry about the connection there, right? There is a robot that has more wheels and that's not a 3 wheels only robot, then you would have to change the kinematics first, the forward. That's mainly what changes from robot to robot. Okay.
Yeah, so
Most
this
of the
is for
code
3 wheels robot.
is for 3 wheels. That's an example
Yeah.
for you.
Okay. And regarding the adding the ultrasonic sensor, the LiDAR sensor, and
Yeah,
so
I'm
on.
gonna show you.
Okay, okay, please.
So we finished the movement part. Let's switch the sensor. I'm gonna give an example. Okay, I'm not gonna do a very deep explanation because most of the information you need you can find in the Studica website there. For example, I wanna use a let's see ultrasonic. You come here, I'm gonna show you C++ for you what you have to do to use the ultrasonic. So what I'm going to show now is more an application that you can apply for most of the sensors. Okay, we're going to create together now the drive, sensor drive, to move your robot using the sensor. Here is using the encoder. So my robot go from position A to position B. Okay, using the encoder. But how about I want to align my robot to the wall using the sharp sensor, using the ultrasonic sensor. Okay, that's what I'm going to show. You could create a new XPP file called sensor. But to make it simpler, I'm going to create the side movement. Let's see. Okay. I'm gonna create a new method inside move.cpp. So just like I have move dot set position, move dot position driver, move dot get x, move dot get y, move dot get h. I'm gonna have a move dot. What I want in the end is a move dot answer driver. Okay. So I need to create this move dot sensor drive inside movement. So what we're gonna do, create the product of the function. It doesn't have a return, so it's void. Because it's inside movement, I need to specify that inside movement sensor. I could create the other files if I want. If I have any input, input will be the distance. How far I want it to be from the wall, for example. And perhaps later. Okay, and then I'm gonna create the logic. Because I'm gonna create the logic here, I need to add it to the header file. Just like I have for the other methods, I need to also add. I'm gonna write down for others. Okay. So now my class knows that somewhere there is a method called sensor drive that is related, is inside the class. Okay, and then later your compiler will find it here. What I want this function to do. I want this function to move my robot while I didn't reach my a condition. Okay, so I will do through a while loop. So everything they have inside the while loop. What's the condition for this while loop? Keep moving until I reach the position I want, the desired position. The desired position is this. It means that I need something to compare to this. I create a new variable. The sensor reading. Start at 0. Start at 0. While I didn't reach this guy. So while
Distance
is
less than distance or greater than distance.
if it's greater than what I want, or if it's less what I want. This true is my tolerance. You can put any number you want. Okay, so it will stop from, for example, here put 16. You go from 13 to 17. So until my sensor doesn't reach this position, I will be reading. Okay. Now where I should get very important now. Now I need to assign a number to this variable. This number that I want to assign be the sensor reading. My sharp sensor, my ultrasonic, my light, whatever. Here, that robot doesn't have ultrasonic, so I'm gonna use a sharp sensor. The same idea for the ultrasonic. Okay. The sharp sensor is a sensor, and I'm gonna specify it inside hardware. Okay. I don't have any function here before sensor, sharp sensor. I have for encoder, I have for cover, I don't have for sharp. So I'm gonna create inside here inside hardware now, not inside movement anymore. Inside hardware, I'm gonna create a function for this function has a return because this function will return the, the number that's being read by the sensor. That will hardware inside the class hardware read right sharp. The sharp goes on the right side. Okay. Because it returned and the return side. Return and what I want to return. What I want to return, I'm gonna have to specify here. So here I have objects for digital inputs, digital outputs, folder, motors. Same way I do for all of them, I need to also do for the analog. for the analog. We can open here this little website to be able to see the short answer. I come to CPP. So what are the things I need? I need here to come back here to make code. And it's library, not already had this guy. I need to actually Studica code. I need to create a constructor. Slide. The same way for digital input, digital output, I'm going to create a guy. There I specify the port, and then the port can either come here and put a number, or to create a pattern, I can come here to my instance. Or to my, let's call it right. Or it's gonna be my case. Let me check. Right sharp and the pink. Okay, right sharp. Here. I can either put two like I did or right sharp. Okay, so now I have the right sharp. Here. Here it keeps the function true. Here. Well, I need to add it harder. This equation here, I don't need for ultrasonic, right? This equation is for sharp only. For ultrasonic, be this guy here. Okay. Same idea, just a little bit different. This equation is because my sharp doesn't return to me the distance. My sharp returns to me a voltage. And I can relate this voltage to the distance that's being read by the sensor through this equation. Each type of sensor, if you take a look at your sensor, there is a model written on it. This model, according to this model, you have a different equation. I have to search on the internet. You put sharp sensor, that code that's written on top of the sharp sensor, and you're going to find the equation you need. Okay. So not necessarily very well for this. Okay, I take this guy here, harder and add this here. So now this guy is part of the hardware class. It means that whenever I call hardware, hard, in this case here, hard dot something, I'll be able to see here, hard dot get. I think it's distance, right? That's very good. Get distance. So now inside the hardware, I have get distance. Whenever I call this guy, it's gonna return to me the sharp sensor. Okay. Where were we? We were in sensor times. Right here. The part. But I think.
Philip, sorry for interrupting.
Yes.
Just a quick question. Now see how you navigated through the constants and then to movement and then to hardware. Can you explain how you do this and what you should put in each file, like .h, movement.h, constants.h, movement.cpp? What should each file contain exactly?
Okay, so let's go. We don't have a specific, that's my pattern. Okay, what you're seeing here, I created, it doesn't come from Studica, it doesn't come from nowhere. I created this way. So I decided to have a code called movement. I decided to have a code called hardware. I decided to have a code called functions. Okay? It's up to your pattern. You can create new CPP files, you can create new header files. How it works in CPP. I have a header file with the declaration where I create stuff, and I have .cpp files where I define stuff. So in the header file, I say that something exists. So here in the header file, for example, .h, I say that position driver function exists. But if you take a look here, I'm not saying what's the shape of it. I just say that this value is similar. That's the purpose of the header file. Once I compile, once I deploy the code, the compiler, you try to find where position driver was created. Where was it created? In my case, because of the way I created the code, it could be created in the .cpp. Here I have position driver and its definition. Okay. Position driver includes movement.h. So whatever exists in movement.h also exists inside movement.cpp. Okay. That header is where I define the proto function of the functions, where I create the classes, where I define the variables and functions. That's the key is where I create itself. It's where I use all this information. You know, for example, because here we are mixing classes with header file. Here, for example, function. I have void.delay. Okay. In functions, I have delay. So it's a simpler version of what we have in the hardware. But here simpler because I don't have a class, right? So it's only a function. So I could add more 10 functions here, but I would have to define that somewhere. Defining function.state.
Uh, Start. Sorry to interrupt, but how do you manage multiple sensors so each works perfectly without conflict?
I've finished the example I'm doing, and shall be deeper. Okay,
Okay.
so let's move on here. So we were here, so all of I made it like a parenthesis to explain how can I add the sensor. So we add the sensor to hardware. Okay. So just like I did for the right sharp, I could do the same steps for left sharp or ultrasonic or Cobra. I think the Cobra is singular. See, Cobra dot get voltage. Okay, same idea, similar to the same idea. So now I'm able to take the sharp sensor information. So I come here, I do hard dot get distance. And so I say hard get distance. If you do right click, go to definition, go to the definition. So it's linked. This guy that they called here is in fact what I just created here. Okay. Okay, and the declaration is here. The definition is in .cpp. Declaration is in the .h. I know that's confusing. That's just but working this way make it more reliable here. Once you get used to the way, you're gonna have much less issues here. Yeah. Basically, I have a class for hardware, I have a class for whatever is related to movement, I put here and add just like it. Whatever is for hardware, you add to hardware, just like it. Okay. So back to our main function here, sensor drive. I have this one loop. Sensor reading now will be updated with the get distance, which is the right sensor information. Okay, and now we can do our logic. Okay, it's a lot of information. That's why we are recording. Later, we can do slowly. What I'm doing here, you can replicate for any function, any application you can create later. So now that I created the sensor, I need to make my robot move. Okay, my robot might move forward or might move backward, according to if my robot's more far or more close to where I want to be. So I'm gonna do a statement if sensor reading is more this means that I want to move forward. Else, how to go forward, how to go backward. I need to say to my robot, what's the combination of motor PWMs that robots need to in order to move?
Mr. Sorry to interrupt you, but
Yes.
regarding the sensors, how does the robot will know which sensors work at a time? Like, is there a specific thing to write so that the robot
Is
will
this
know?
function here? You see, get, I will change the name. Get right distance. Okay? Yes. Get right distance. So from now on, every time I call the function get right distance, I'm talking about the right sharp sensor. And right sharp sensor is talking about this right sharp sensor, which is the pin number 2. So every time I call get right distance, I'm reading the sharp number 2. If I want to create for another sharp, I want to create for left sharp or left tonic or whatever, I would have to create it here. Okay, specify the pin, I will remove it. Let's see. Okay. So my right sharp is on pin number 2, my left sharp is on the pin number 3. I iterate it here, that effect time, paste, and take left. And then also change the name. So now I have the function get right distance, get left distance. Whenever I create a new function in a class, I need to insert it to the class. Say that in like 7. So now I have the function get right distance, get left distance. When I call right, it's gonna read the pin number 2. When I do get left distance, it's gonna read the pin number 3. Okay? So if here in my code I do get right distance, it's gonna read the pin number 2, which in my case is the right side. If I change here to get left, read the pin connected to the pin number 3. If I want to read more than one sensor, I could just put here.
And for the motors, how they are being controlled?
I showed before in the beginning. That's the same idea. Here I have hardware dot set left, set back, set right. Same idea. There inside hardware. And inside hardware, I have the function set left. Applies a PWM to the left motor. Who is left motor? I come to hardware, left motor is this one. This guy is attached to the pin left motor, which is pin number 1. It's a complicated way to do something simple, I know. But later, to create the idea of C++ is to create the codes hard, but to maintain, to change, to use is easy. So whenever I want to just change the pins, I just come here and put them here. I don't need to analyze my code. I just come here and change the pins. Okay. But for example, left motor is 1. It means that I could come here, remove this entire guy, put 1. Same. Okay. So left motor is the motor connected to the port 1. So when I come here to hardware.cpp, set left, I'm gonna set the PWM, the motor connected to the port 1. And then I can use this function set left to my movement.cpp and apply any PWM. Okay.
This one means the M1 on the Titan quad, right?
Yes. So one is here. One is M1. Back motor. Back motor. Back motor is M0, right motor is M2, elevator motor is M3. And that's why it's important to change these numbers according to your output. But don't change it here, and for some reason your left is disconnected between your two. You're able to rotate the left, thinking that's rotating the right, or thinking that's rotating the elevator, or thinking that's rotating the left. The first thing you have to do is to make sure that the things that are specified here are the same as your own. Okay? Let's finish our function. Here. So now if sensor reading, what my sensor is reading is more than the distance I want, to go forward, I could, in a simple way, for example, I could come here. We know that to go forward, I need to move left and right. So what I could do is, if my sensor distance is greater than this, I want to go forward, I can come here and put 0.5 left, minus 0.5 your right. So my left will rotate forward. So my left will rotate forward, and my right will also rotate forward. My back will be stopped. So my right will go forward. And then here also I will do the opposite. Okay. That's the simplest way. If you are confused, you can use this way. If you are not confused, you can use the other way. That's Philip's way. Which is, you can follow my first kinematics. It specifies the desired x, y, t, h, and according to it, it defines how much applying each wheel to perform this move. It means that if I want to go forward, I need to apply speed in x. Backward, minus 1. First kinematics, we calculate how much should be applied in terms of PWM to the wheels to perform this move. After burst kinematics calculate these guys, I need to apply to the motors, and then I can clock paste. Same as I have mentioned. Okay. If I press the start button, I stop the motors. Okay, so if the stop button is pressed, the robot is on. Otherwise, apply to the set left, desired left speed, set back, desired back speed, set right, desired right speed. Where the desired left speed came from kinematics. And kinematics took the x 20 and translated this plane into back left, and right. Okay. And that's it. Easy. Well, it's not easy. That's what we need. And once we do it once, we don't need to worry about it. Every time I have a while loop, I need to put a delay to avoid it to get stuck anywhere. And after finishing the loop, I make sure that the wheels go slow. I will build to make sure we didn't get any error, just to check if anything is seen. Now build is going to compile, so it's going to check if we didn't miss, if we didn't forget anything. Since that, okay. Once I created my function sensor drive, here. So now I create my sensor drive. What does it do? Take a desired dist, check if my sensor reading within the range that I want. 15, so it goes from 13 to 17. Updates the sensor reading. Determines if I should either go forward or backward. If I press stop button, I stop. If I don't press, I'm gonna move according to the inverse kind of things. If upwards, we should update the variables and the delays and the order. Pass, and then after pass, you guys can pass. 5 minutes. It's not sure like sensory or so essentially that's get right distance. Drive to 15, set to 0. Off. I don't know if you guys saw, stopped, right? If you move a little bit and then stop. Stop once it reach 15. I'm gonna run again. I'm gonna put my robot closer than 15 now. And then my robot moves backward. Moves backward because of the state. Yep. I don't have side move, I don't have side sensors. Okay, but let's say I want my robot to go left and right instead of X, B. Here it is to the left. Right. Gonna have to use the current sensor instead of side. And that's it.